morning, everybody. Well, I think I'm going to talk about a different approximation to understand what is happening in space and in astrochemical environments. And the approximation we are using is laboratory astrochemistry. So basically, we simulate in the laboratory some processes that are occurring around AGB stars. Today, I will talk basically on the formation of cosmic dust analogs starting from atomic carbon. And all these results have been obtained within the European project that is called NanoCosmos, that is funded by a European Research Council. And here you can see a cartoon of a webcomic that has been done based on our project, and I think it's a nice introduction to the project, and you can enjoy reading it here. So, okay, the outline of my talk will be as follows. First, I will make a brief introduction of cosmic dust formation in space and how we can simulate it in the lab. Basically, I will introduce the Stardust machine that we have built within this project. And then I will focus on our recent results on the production of cosmic dust analogs, starting from atomic carbon, from its interaction with hydrogen and with acetylene. And if I have some time, I would also like to draw you the attention on our very, very recent results on the interaction of silicon and hydrogen. So let's go. So where is cosmic dust formed in space? Well, mainly, not only, but mainly it is formed in red giants, in the so-called asymptotic giant branch stars. And these stars start pulsating and starts emitting atomic elements heavier than helium, such as carbon and oxygen. And then in the inner envelopes starts a very rich chemistry that leads to the formation of several chemical species, such as CO, water, so on. And at a certain distance from the star, the conditions, the physical-chemical conditions are appropriate for all these molecules to aggregate, forming solid material. So they condense, forming dust. Depending on the star, the material, the composition of this material, of this dust, is different. So in the so-called oxygen-rich stars, that means that oxygen is in excess to atomic carbon. Mainly, the composition of the dust is mineral. They are mainly formed by silicates. Whereas in carbon-rich stars, meaning that carbon is in excess of oxygen, the material is basically carbides and some kind of carbonaceous material. All this material, the molecules and the dust, they continue their expansion towards the interstellar medium and the outer envelopes of this kind of stars. Cosmic rays from the galaxy and ultraviolet photons can penetrate, and then a different chemistry starts that is mainly driven by photochemistry. Okay, whereas the composition of silicates and carbides are very well constrained, the composition of this carbonaceous dust has been under debate for the last 20 years or so, and different models have been proposed. Probably the most accepted one is this one that considers that the dust is formed by the aggregation of this kind of structures that we can see here that are mainly, it contains mainly polycyclic aromatic hydrocarbon domains linked by some aliphatic bridge. But there is a problem, that is that neither benzene, that is one of each of these rings, benzene, and nor a single polycyclic aromatic hydrocarbon have been identified in carbon-rich stars. And this have led to propose other different models that can account for the carbonaceous cosmic dust formation. Being most probably, some authors suggest that it is formed by amorphous amorphous hydrogenated carbon. That is a complex amorphous mixture of carbon in sp2 and sp3 configurations with different degrees of hydrogenations. And also these kind of extractors that are called mixed aromatic aliphatic organic solid materials have been proposed. Okay, apart from observations, the other possibility that we have to try to know what is the composition of the carbonaceous dust is by simulate its formation in the laboratory. Okay, and the usual methods that have been used for this are plasmas or laser ablation or pyrolysis. The approximation we have used is a completely new one that is based on the use of sputter gas aggregation sources. I will briefly describe what this means. Okay, but it's a new approximation that allows the direct condensation starting from atomic precursors in a similar way as it occurs in the stars. Basically, in these sputter gas aggregation sources, what one can do is to vaporize solid elements. In the case of carbon, we are using graphite. Okay, we vaporize, we extract carbon atoms, and we let them interact among them inside what is called an aggregation zone, where all this material is condensed into nanoparticles. So material of size of around 10 nanometers. And all this material that we synthesize here is afterwards extracted through differential pumping, so with different pressure here and here, and forms a jet of flying nanoparticles, so a beam of flying nanoparticles. That is what we consider our analogs. Okay, this is the main technique, and as I have said, we have pioneered in the use of this technique to mimic the formation of cosmic dust, and is the main synthesis technique that we use in a unique facility that we have developed within the Nanocosmos project to try to mimic to understand cosmic dust formation in the circumstellar envelopes of AGVs. Okay, what you see here is just the drawing of the machine, the technical drawing. So, as I have said, the first part is just this a kind of aggregation source that is called multiple ion cluster source that produces a nanoparticle beam that travels along the rest of the machine. Okay, so here is where we synthesize, we fabricate our analogs. Then we have a module that is just for diagnose all the properties of this beam of nanoparticles. Then afterwards we can process in flight this material. Basically, we can heat it up to temperatures close to those in the dust nucleation region of AGVs, and we can also accelerate the flying analogs by means of electromagnetic lenses and so on to simulate the radiation pressure that accelerates the cosmic dust in AGVs. Finally, we have two more modules. One is, these are dedicated to analyze all the processes and the material. Basically, there are two. This one here that you can see integrates infrared spectroscopy and also has a cryostat, so we can also simulate the formation of icy mantles on the surface of the cosmic dust. That is something that happens in molecular clouds. And the last module is just analysis by electron spectroscopies and thermal program desorption. Okay, this is how it looks in reality. So here you can see the module for analog production, the diagnosis chamber. This is the oven. This is the processing for accelerating. This is the chamber for analysis by infrared spectroscopy, and this is for electron spectroscopies. I want to stress that all the process is performed in ultra-high vacuum conditions. So this is the base pressure of the system, what ensures that we have a very good control on all the production parameters, and the environment in which we synthesize these analogs is ultra clean. So concerning the capabilities of the Stardust machine in terms of nanoparticle or cosmic dust analog production. The modified sputter aggregation source, this specific kind that we are using, has inside up to 3 different targets, meaning that we can vaporize at the same time up to 3 different elements. Apart from that, we have designed an additional gas entrance, so we can inject gases inside the aggregation zone where all these all these atomic elements are vaporized from the targons. We can inject gases, and we can also perform optical emission spectroscopy. Okay, these are just some examples on what we have done based on pure elements. So we are able to produce pure silicon nanoparticles, or pure iron, or pure carbon. Okay, as is reflected in the title of my talk, today I will focus on carbon, on atomic carbon. So, okay, the first result I would like to present you is our paper that has been published this year in Nature Astronomy, and that deals with the interaction of carbon and molecular hydrogen. Okay, the novelty of this work has been highlighted by the journal with news and views. So what have we done? Okay, we have injected hydrogen inside the aggregation zone of this machine, and we have done it with 2 different densities of hydrogen. Okay, this is the number of carbon atoms, the density of carbon atoms that we extract, what we vaporize from the solid target, and we have used 2 different densities. A low density, what we call low density, that means that is more or less on the same ratio of carbon. And this is the density that is found at 2-3 stellar radii from the star. So it's in the dust nucleation region. But in order to be more realistic in terms of the carbon to hydrogen ratio, we have used also what we call the high density dose, that is more realistic in terms of that hydrogen is much more abundant. Okay, so this is the kind of morphologies that we have observed. So spherical nanoparticles around 9 nanometers in diameter. But if we have a close look on these regions, these are microscopy images on these regions that they look empty. If we zoom in, we start to see that there are still some structures. If we zoom in even more, it seems that there's a kind of mantle of material that we cannot resolve with this microscopy. So we have performed a much more powerful microscopy, that is scanning tunneling microscopy. And we have observed that in these regions, we have some kind of molecules that we start to resolve, that we identified as short carbon chains with 3 to 5 atoms of carbon. But okay, which is the chemical process that leads to this? Okay, for that we use optical emission spectroscopy, and when the amount of hydrogen that we injected was really low, what we observe is just the presence of diatomic carbon through the optical emission, the so-called Swan band, but nothing on the emission of atomic hydrogen. However, when we injected more hydrogen into the system, what we observe is that the C2 band, so the diatomic carbon, completely vanishes, and we start to see the emission of atomic hydrogen. And this gives us the clue that the main chemical process is this one, so the formation of the C2H radical. The next thing that we did to understand the chemistry is to perform mass spectrometry in flight, right after the formation of these analogs, and we observed several organic molecules such as methane, acetylene, ethylene, up to propane. But the important point here is that we did not detect benzene, nor toluene, nor any other aromatic. To try to understand these processes, what was happening here, we performed some chemical kinetics modeling of all the chemistry, and we identified these as the key reactions. So the formation of diatomic carbon from atomic precursors, and the formation of CH2 that starts to promote the formation of all the hydrocarbons that we have observed. Okay, but this is for the gas phase. What about the solid phase? Okay, so for that we perform a kind of mass spectrometry that is called laser desorption ionization. Basically, you warm up your material with a laser and you perform mass spectrometry of the gases that you extract from these laser pools. And this is a technique that is extremely sensitive to aromatics. And even though this technique, as I have said, is extremely sensitive to aromatics, what we observe is that the solid analogs are formed basically by pure carbon clusters, hydrogenated carbon clusters, and aromatics represented less than 3% of the material inside these dust analogs. And this has led us to conclude that aromatics cannot be efficiently formed in the circumstellar envelopes of AGVs. In fact, as I have said, nor benzene nor a single aromatic molecule has been detected in circumstellar envelopes. But polycyclic aromatic hydrocarbons are widespread around the galaxy. So we propose that a method in which these molecules can be formed is by the catalytic recombination of these small hydrocarbons that are formed in the star on the surface of dust grain. For that, the clue that we have that this can be like this is by temperature program distortion. What we do is just we collect our dust analogs on a surface. In this case, it was gold. Gold is known to have some catalytical activity. Okay, and we warm it up. And while we heat it up at around 100 degrees C, we start to see the signal from benzene and from naphthalene. And this is what gives us the clue that, okay, aromatics cannot be formed efficiently in the circumstellar envelopes, but processes at the surface of the dust can lead to the formation of polycyclic aromatic hydrocarbons. So the second results that I would like to show you have been published also this year, and is the interaction of carbon, C2, and acetylene. Okay. Acetylene, the interest of acetylene is that it is the most abundant hydrocarbon in carbon-rich stars. Okay, and although we have seen, well, it is believed that acetylene is involved in the formation of aromatics, but as I have shown previously, the interaction of carbon with hydrogen is not enough to promote enough formation of acetylene that will lead to the formation of aromatics. Okay, but we were interested in studying the chemistry, even if it's not the main process in carbon-rich stars, and for that we increase on purpose the amount of acetylene with respect to atomic carbon. Okay, in the stars in the dust nucleation region they are more or less on the same abundance. Okay, but we have increased it 2 orders of magnitude. This is the kind of morphology. So time is running really fast. This is the kind of morphology that we observe. So they are nanoparticles. If we go to another microscopy, it's an amorphous material. Doing the same, we perform optical emission spectroscopy inside the aggregation zone of stardust. So when no acetylene is injected, we just observe the formation of diatomic carbon, no atomic hydrogen. But as soon as we inject acetylene, C2 is consumed. We observe the emission of atomic hydrogen and also a small band that can be assigned to the CH radical. So we identify these as the possible chemical reactions leading to the consumption of diatomic carbon and the appearance of the emission from atomic hydrogen. As in the previous case, we perform mass spectrometry. Okay, in this case, even with higher sensitivity, and we observe first just a kind of polyacetylenic chains. This is known for the polymerization of acetylene, but in this case, we did see a lot of aromatic molecules that are labeled here in blue, but not only aromatics, but also aliphatics that are labeled in green. Okay, we have tried to rationalize all the chemical equations, all the chemical reactions involved. Okay, for the formation of polyacetylenic chains, this is driven by the acetylene polymerization, that is a known process mediated through these two radicals. I remind you that C4H was formed starting from the atomic carbon. In the case of aromatics, we suggest that they are formed by the so-called hydrogen abstraction acetylene addition mechanism. That is a known process, and we also observe some key intermediates on this reaction. So that points towards the Haka mechanism. But here, the interesting point is that there are other aromatics with aliphatic substitutions, like these ones that I highlight here, that are not predicted by the Haka mechanism. And we rationalize the formation of this species through a process called methyl addition that is mediated through the formation of a methyl radical that might come from the detected CH, and also the formation of carbon clusters without carbon number of atoms, okay, starts from atomic carbon. So the particularity of adding atomic carbon to the system is really that we have the formation of aromatics with aliphatic substitutions and a good amount of carbonaceous clusters, both pure and hydrogenated. Okay, this is just what happens to the solid phase. I'm running out of time, so I will not go into details, but okay, this is infrared spectroscopy, and we see some bands that are assigned to sp carbon, others to aromatic sp2 carbons, to olefinic sp2, as well as aliphatic sp3 carbons. So, and also this broad band corresponds to amorphous carbons. So our analogs are really a complex mixture of sp, sp2, and sp3 hydrocarbons along with amorphous carbons. So all the material, all the gas phase species have been really incorporated into the analogs. Finally, as I have mentioned, I would like just to draw your attention on our recently accepted paper in Astrophysical Journal, and it's about the chemistry of silicon, atomic silicon and hydrogen, which is interesting also in carbon-rich AGVs, as can be derived from the detection of these silicon-bearing molecules. And okay, we have synthesized these processes, and we have observed a nice process that can be an additional source of silane, and this silane, that is the thermal processing of amorphous hydrogenated silicon. And with this, I would like just to give you my take-home message. I hope you have seen that the Stardust is a very versatile setup for the simulation of the circumstellar envelopes in AGVs, and we're open for collaboration. I want just to acknowledge all the funding and all of you for your attention.
Thank you. Thank you.
May I ask question? Okay.
Yes,
Sure.
yes, Professor Ethan.
Yes. Thank you for your presentation. And can you explain the discrepancy between observed wavelengths of diffuse interstellar bands and wavelengths of supposed carriers from laboratory spectra? As far as I know, there is no agreement at all.
There is no agreement. Yes, I mean, it's not. Well, first of all, I'm not astronomer. I'm not an astrophysics, so if I make some
but you mentioned
mistake.
some astronomical data, input data about AGV stars.
Yes, what is not detected inside AGVs is benzene. Benzene and aromatics are detected in protoplanetary nebula, but not in carbon-rich stars. So the idea behind is that the formation of benzene and PAHs must be in a kind of evolutionary scenario towards the protoplanetary nebula, but not the formation directly in the carbon-rich stars. Maybe driven by photochemistry, I don't know. What we propose, and these are, of course, these are simulations in the laboratory. What we propose is that there should be some catalytic activity of the dust. Probably, we have not proved it, but my opinion is that probably iron-based. Iron is also a kind of good catalyst that will promote the formation of aromatics from aliphatics. We're still working on this. Of course, it's not an easy issue, but we collaborate also with astronomers.
Maybe the problem is, can you, for example, create negatively charged atoms, molecules in your aggregate?
Yes, in principle, there's a way. It's not easy, but there's a way to control also the charge. Most of the chemistry inside the aggregation zone, and this is the particularity of this technique, is that most of the chemistry goes via neutral reactions. So this mimics better what is happening in the inner envelopes of the AGV stars. For example, in comparison with plasmas or laser ablation, the chemistry is driven really by ion neutral reactions. There is a way, it's not easy, but we can somehow control the charge on the nanoparticles. And to some extent, so we can apply some electrical fields, to some extent also on the molecules, but this is even more difficult. But
Thank you.
It would be great, of course.
Okay, thank you.
You're very welcome.